Hi, my name is Benjamin Bradshaw. I'll be presenting on a wave-controlled reconfigurable intelligent surface today. I'm a second-year PhD in the computational science program. I work in the Department of Electrical Engineering. My main advisor is Professor Filippo Capolino at UCI, with a co-advisor of Professor Satish Sharma at SDSU. My co-presenter today is Miguel Mello, and in Professor Capolino's lab as well. I'm going to be presenting on research problems that I have had with association with this new device being developed at UCI. A reconfigurable intelligent surface is made of an array of antennas or an array of meta-atoms called a metasurface, and I'll continue presenting on reconfigurable intelligent surfaces on the next slide. These reconfigurable intelligent surfaces are called RIS for short. They are made of a bunch of unit cells, as discussed before, that are dynamically tunable, and they are used to control the reflection of incident electromagnetic radiation. There's many different applications, but I'll be talking about beamforming with regards to our reconfigurable intelligent surface. Our design for the wave-controlled reconfigurable intelligent surface is one that can also control this reflected radiation by this array of antennas on this top layer. This picture on the right is the design that has been developed so far at UCI. This top layer is a layer of a bunch of patch antennas, which are able to beamform, as shown in this picture on the top left. This graph is the beamforming that's done by the surface, directing a beam in the 30-degree direction. The novelty of our design, however, is that each of these elements require a bias network to apply a DC bias to each of the elements. However, we've designed a transmission line. Instead of having to have a specific transmission line that is connected to each single element, we've designed one single transmission line that can be connected to all of the elements, on which we excite standing waves. And from these standing waves, we can optimize so that we'll have specific DC biases at each antenna element. These standing waves are excited by this waveform generator as seen on the left. And onto my current research. There are two problems I'm trying to solve with my current research problem in the RIS. Both of them have to do with the phase of the element, as the phase of the elements of the reflected radiation off of these elements are what's used to beamform off of this surface, and it also controls the bandwidth of the surface in general. First, the beamforming problem is the problem that we have to match our desired standing waves to the desired beamforming pattern that we want. We can match this as we know that we'll have a desired voltage output at each element to create desired phase output or phase reflected from that element. The standing waves from the surface at each position can be seen in this first equation. At each element, there's a circuit called a rectifier that converts these standing waves into a DC bias voltage. And this circuit effectively takes the maximum at this position through time of these standing waves. And then the cost function is matching the desired voltages for our beamforming to the output voltages from the system. And we have a non-convex problem due to this maximizing function. Currently, only local optimization solutions have been applied to solving this problem. Then onto my dual resonant element research. These RIS elements require 360 degrees phase shift from each element to be able to do the desired beamforming. But the problem with a single resonant element is this phase shift is often less than 300 degrees for a wideband element. And to be able to design a more wideband RIS, we've been focused on designing more wideband and dual resonant elements, which will have greater than 360 degrees. I'll be presenting this and more at the ACSESS presentation at the end of March. Hope to see you there.